urgent, analytical. For the last 5 years, building AI was a simple exercise in volume, but brute force scaling has hit a hard physical limit. The strategy that dominated from 2020 to 2024, stacking more parameters into a single network and scraping the internet for raw text, is mathematically exhausted. We have reached a critical paradox. Models are finally demonstrating advanced reasoning, yet the computational cost to achieve marginal improvements has grown exponentially. Pouring more compute into monolithic architectures simply doesn't yield the capability jumps it used to. In response, the industry is pivoting toward an engineering phase researchers call structural refinement. To break through the current performance ceilings, engineers are systematically decoupling and unbundling the tightly integrated systems of the past, separating logic from memory and physical reasoning from semantic instruction. The intelligence of the next generation of models will not be dictated by their raw size, but by the structural elegance of a decoupled architecture. Every theoretical breakthrough in machine learning ultimately relies on the physical infrastructure of a data center, and at the silicon layer, training and running AI is no longer a math problem, it is a memory bandwidth problem. This diagram illustrates a standard GPU during autoregressive text generation. The actual computing units, the ALUs and tensor cores, are only actively calculating about 10% of the time. The remaining 90% is spent idling, waiting for massive neural network weights and the KV cache to squeeze through. To speed this up, designers would ideally stack these components vertically. But researchers at KAIST have pointed out a physical paradox. The extreme heat generated by dense logic units requires massive cooling plates on the back of the chip, blocking any physical space. Standard logic routing has hit a rigid thermodynamic wall. To move forward, compute hardware must be unbundled from the constraints of a flat two-dimensional grid. A theoretical framework introduced in Huawei's Tau Law v2 provides a blueprint out of this deadlock. It abandons the traditional practice of macro-level discrete optimization, where engineers simply stacked large functional blocks like SRAM on top of logic cores. Instead, the design shifts to what they call logic folding, a method of continuous optimization down at the individual cell level. By utilizing a specific gear ratio engineering approach, designers are now crossing physical bonding layers at a microscopic 1.5 micrometer pitch. Rather than treating the chip as discrete flat layers, individual logic cells decouple from the 2D plane and begin folding upwards into continuous three-dimensional space. Because the data pathways now move vertically, the physical route between logic units is a fraction of the distance required in older 2D routing. This drastically reduces the interconnect delay without generating the heat that causes thermal meltdown. By unbundling standard routing and exploiting continuous 3D space, hardware engineers have engineered a verified detour around the thermal limits of the post-Moore era. While hardware was constrained by thermodynamics, the software layers suffered from a separate issue. The massive compute waste of the early 2020s was severely compounded by a foundational software bug in the original scaling laws. This chart plots the loss curves from the 2020 Kaplan scaling research. Notice how the performance line flattens out toward the end of the training run. This occurred because researchers unified their models with a hyperparameter choice called cosine learning rate decay to 0. Forcing the learning rate to drop to 0 completely stops the model from updating its weights. This creates a false mathematical signal, making it look like the model has hit a saturation point, when in reality it still has the capacity to absorb vast amounts of data. This false saturation metric tricked the entire AI industry. For years, labs threw millions of GPU hours into training massive, oversized parameter models that were actually severely starved of training data. Attempting to fix this data starvation by generating synthetic data isn't a silver bullet. Recent findings from the Shanghai AI Lab reveal that synthetic data generation eventually hits a hard entropy limit. Using a language model to endlessly rewrite the same source texts, a process called fixed source synthesis, merely interpolates existing information. It is mathematically incapable of generating out-of-distribution, novel knowledge. The blind pursuit of volume scaling created a multi-year illusion, masking the technical shift required in model alignment and reward allocation. This need for structural reform is glaringly obvious in visual generation. When researchers apply standard reinforcement learning to align image models with human feedback, they run into a distinct failure state. It is known as mode collapse. The model discovers that one highly saturated, specific aesthetic consistently scores high. It aggressively optimizes for that exact visual manifold until every output it produces starts to look exactly the same. To solve this, researchers at Tencent Hunyan structurally decoupled the reward system itself. This diagram compares the two approaches. On the left, a standard system judges individual, isolated images. On the right, the new framework evaluates an entire batch of generated images simultaneously, measuring their collective variance against real-world data using a metric called Wasserstein distance. By measuring the distance at the distribution level, the system forces the model to generate a batch of images whose overall variance perfectly overlaps the exact shape and density of the real-world data manifold. Because calculating high-dimensional distances on massive batches is computationally brutal, they employ a subset-replace strategy, updating only a small fraction of a long-standing reference set during each step to keep costs viable. Separating the evaluation of a single sample from the variance of the whole distribution prevents reward hacking. It is the mathematical solution required to align generative AI without destroying output diversity. This same philosophy of unbundling is now moving from digital software into the physical world of embodied AI. Currently, training monolithic vision-language action models requires millions of wildly expensive human teleoperated demonstrations. This visual equation displays the required dataset tensor. A high-quality camera view, a natural language text instruction, and precise mechanical joint angles are all fused into one rigid block for training. Fusing these elements creates extreme brittleness. If you shift the camera angle by just a few degrees in a real environment, the model's success rate will plummet to 0. The system fails because researchers are forcing a single neural network to simultaneously learn two entirely different objectives: the physical laws of how to move and the language-based semantics of what to do. As long as physical motion and language processing are chained together in a monolithic architecture, robotic AI will remain economically unscalable. To solve this data wall, researchers at Fudan University introduced the TAP framework, a method that structurally decouples these two conflicting learning objectives. In Phase 1, they isolate the kinematics. The network trains entirely on unlabeled, random physical interactions, discarded trajectories, and unstructured grasps, without any human text instructions. Using an objective called inverse dynamics, the network learns to predict the motor torques required to transition the environment from one visual frame to the next. Through this, the robot internalizes a robust physical prior of its own mechanics. In Phase 2, semantic alignment occurs. A tiny fraction of expensive language-labeled data is finally introduced to direct the already capable motor system. The results of this unbundling are staggering. Under extreme visual perturbation, where mainstream monolithic models collapse to a 0% success rate, the decoupled model maintained 25% zero-shot robustness. Decoupling physical instinct from semantic instruction provides the only verified method for scaling generalized embodied agents. Synthesizing, forward-looking, across the entire technology stack, these decoupling strategies are converging, from 3D silicon at the base to the separation of movement and language at the edge. While scaling continues, the industry's reliance on raw volume is yielding to a focus on structural efficiency. This intelligence per token is becoming the dominant metric for performance. But this structural evolution introduces a severe security risk. As these highly optimized models transition into autonomous agents with write access to enterprise databases and environments, the blast radius of any failure escalates exponentially. Recent evaluations from the Vera testing framework demonstrated an alarming attack success rate against production-level agents. Furthermore, incidents like the hidden steganographic spyware discovered inside the Claude Code developer tool, which secretly tagged users based on local time zones, have exposed the inherent vulnerabilities of trusting third-party black boxes. Because these advanced agents require deep execution privileges on local machines to function, the trust required to run them is eroding. The once borderless, open-source AI infrastructure is now fracturing along geopolitical lines. For the modern engineer, the frontier has shifted. Success is no longer measured by managing massive parameter counts. The urgent task now is architecting precisely decoupled intelligence systems
that operates safely within zero-trust, air-gapped runtimes.